In this video demo, we are going to present Arbitrar, a tool that helps regular programmers to quickly identify API misuse bugs through fast user interaction. This demo will have 3 sections. We will first demonstrate how you can set up an analysis database with our tool. Next, we will show with examples how an end user finds API misuse bugs. Last but not least, we will show an interesting use case and talk about our future plans on extending Arbitrar to handle even more real-life scenarios. We start using Arbitrar by creating a brand new database. We first make a new DemoDB directory. Inside the directory, we run arbitrar init to initialize a new database. Arbitrar can operate on any library and programs written in C or C++. For Debian packages, we have an easy command line interface where you can simply type arbitrar collect OpenSSL to add OpenSSL into the database. To add a list of packages, you can create a packages.json which looks like this. Inside, you can specify any Debian package or Git repository. Simply type arbitrar collect packages.json to collect all packages into our database. You can also add a precompiled package. As a prerequisite, arbitrar requires the code to be compiled into an LLVM bytecode. In this example, we have precompiled a Linux kernel, as you can see with this vmlinux.bc. We use the command arbitrar collect directory/vmlinux.bc to add this precompiled Linux kernel into our database. If we now run the command arbitrar query packages, we see that our database now contains 4 packages: OpenSSL, libpng, optpng, and vmlinux. After setting up our database, we talk about how we use Arbitrar to find API misuses. We pick our first example to be a very commonly used API by libpng-related packages, png-malloc. Although this API is widely used, it is also very widely misused. Just like malloc, this function allocates a PNG buffer pointer. When the allocation fails, it will return a null pointer, making the subsequent pointer dereference very dangerous. Therefore, a correct call to png-malloc would involve a null check right after. In the bottom example, we have a clear misuse of png-malloc as the returned pointer is not properly checked. Now, let's see how we would use Arbitrar to find the misuses of png-malloc. First, we want to let Arbitrar analyze the use cases of png-malloc to build a foundation for our future interaction. After this process, we can type arbitrar learn active png-malloc to start the user feedback loop. Let's first take a look at the user interface. Here, you see one use case of png-malloc in the source code. Our target API call, png-malloc, is marked in orange, and the execution trace is marked in green. Notice that we ask a question to the user, do you think this is a bug? And we let the user provide yes or no feedback by simply typing Y or N. We are actually very lucky here that the first use case presented to us contains a bug. The result from png-malloc is not being checked properly right now, so we type Y to tell Arbitrar that this use case contains a bug. Now we have moved on to the second trace that Arbitrar presents us. Since we marked the first use case as bug, Arbitrar learns from the previous feedback and is now proposing a new use case that has a pattern very similar to the bug. In this case, we are indeed encountering a bug again as the result of png-malloc is still not being properly checked. In fact, this process continues for one more interaction where we encountered the third bug. After marking it, we start to see traces where the result of png-malloc being properly checked. In this case, we will provide a negative feedback by typing N. With one more non-bug, we are confident that continuing interacting would not yield any more bug to us, so we hit Q to exit the interaction process. This procedure indeed finds us all three true bugs with PNG malloc in our database, and the fact that we find all three in very early stages is a very nice demonstration of the effectiveness of our tool. Next, we look at a slightly more complicated function PNG create info struct. This time, not only its return value should be checked, the argument of it should be checked as well. Without further ado, let's step straight into the user interactions by entering the command arbitrar learn active png create info struct. The first trace we encounter is a good one, where we see both the return value and the argument being checked properly. Therefore, we provide a negative feedback saying this is not a bug. But then, right off the bat, we see that the second trace presents a bug. The argument is not being checked before our target API function call. This pattern actually continues for 2 more iterations, and we claim all 3 are bugs. From here, we have explored all the buggy traces, and we are getting back to the normal traces where both return value and arguments are checked. After seeing those traces for a few rounds, we are again confident that no more bug will be found. We will then hit Q to exit this process. We demonstrate one final example, clock prepare lock. This API function is extensively used in the Linux kernel, and every time you use this, you should make sure that clock prepare unlock is also called. Again, since we have done the analysis step with this function, let's dive straight into the user interaction with arbitrar learn active clock prepare lock. For the first 4 usages it proposes, they are all correct usages where the clock prepare unlock are properly called afterwards. But when the learning algorithm collected enough signals, at 5th attempt, it proposes a true bug to us. From the source code, one can see that if the execution goes into the if branch, this function will directly return without calling clock prepare unlock. In conclusion, we can find this true bug in the 5th attempt while arbitrar tries to learn the specification of this function completely from scratch. In summary, we showed an easy and intuitive user interaction scheme that empowers end users to find bugs effectively. What's more, we demonstrated that our interaction is real-time, which makes the bug finding and the interaction process less of a burden for regular bug finders. Most importantly, we showed that arbitrar can identify API misuse bugs quickly and precisely within just a few rounds of user interaction. We now talk about one interesting use case of our arbitrar framework. Oftentimes, people already hold one true bug as an example. With arbitrar, you can easily utilize this known bug and make the bug finding process even faster. As an example, in an evaluation on bnctxget, a function of OpenSSL, due to its complex specification and wide range of use cases, arbitrar can only find the 3 bugs in the 13th, 14th, and 15th iteration. But if one of these bugs are presented as a known bug beforehand, we can find the other 2 bugs right at the beginning. Just like this interesting scenario where one bug is provided, we really want to fully utilize the extensible nature of arbitrar. For example, we can integrate arbitrar into continuous integration. This allows incremental bug finding where the knowledge of API misuse bugs can be accumulated over time. We can also enable transfer learning where we transfer the knowledge we learned from one API function to another API function. This way, we can reduce the number of human labeling effort. And there are many more. In conclusion, arbitrar is a highly usable, scalable, intuitive, and extensible API misuse bug finding tool. We are proud of what we can achieve right now, and there are more to come in the future. Thank you.